Welcome back to Turing Complete. Where we last left off, we had just learned about multiplexers and solved the bus level. Let's move on to the saving gracefully level. The delay line only allows us to save a value for one tick, but sometimes a component that can save a value for longer periods of time is useful. We want you to build such a component. In this level, you have two inputs. When the first input is high, update the saved value. The second input is the value. Always output what is currently saved. This is a diagram of the component that we want you to build. We'll have a save enable input, a save value, and an output. Check this hint if you get stuck. Okay, so let's start by thinking about previous levels that we've done. In this case, we're trying to select between the currently saved value and the new value, but only if the save action is toggled on. This sounds kind of like our multiplexer. Now, this is single bit, so we can't use the mux that we unlocked here, but we can use the same exact things we used to make the mux, these switches. So let's go ahead and get some outputs here and let's label these. We're gonna have a save input right here. So this is the wire that's gonna output high if we want to save. And this is gonna be our value to save, the new value. Now let's look at this delay line. Now this is going to take whatever is on this input right here, and it's going to delay it by one tick. So whatever's right here, this is essentially the saved value. Whatever's on this wire is going to get passed through to the next tick. So let's start by thinking about the case where all we're going to do is pass through the currently saved value if we don't try and overwrite with a new saved value. So the first thing we're going to do is we're going to just loop this right back around to the saved value. So the way that this is currently set up, whatever the output of this delay line is would just get fed right back in, and it's this currently saved value here. But we only want to do that if this saved value is low. So let's instead connect this up to this switch here. So if this save action line is low, that should control whether or not this gets passed through. So let's take a NOT gate and connect this up to here. So if this saved value is low, then this should turn on, allowing whatever value is on this line to get passed through into this saved value and output on the next tick. Conversely, we want this value to get passed through into this saved value if this save line is positive. So we can just take the output of this, pass it through there, and this, if I toggle this, now that's going to allow this value to go through here into this saved value here. And then on the next tick, it would save, and there it goes. If I turn off the save and turn off this value here, it should stay positive. Oh, it was going through the different scenarios automatically. It looks like that completed it. That unlocks the 1-bit memory. All right, we've got memory now. My goal today is to complete all the levels to get up to this line here, so we finish off the arithmetic and the memory section. So I'm going to tackle CPU architecture next episode, so let's finish off arithmetic and memory. Saving bytes. Create a circuit that can save or load a byte. When the first input bit is high, load the memory and send it to output. When the second input bit is high, save the input byte. The output has an enable pin, enable it only on load. Alright, so it sounds like we're trying to make 8-bit memory here. Okay, so that's our input values going into these save values slots of these 1-bit memories. Now we need to connect our input here. We want this to save only when this input 1 is toggled on. So let's just connect up our save toggle up to this top here, which is going to be our save values. Okay, now if this is saved, then on the next tick it should save that to the output as well. Now let's think about the loading. We should load only if this load input is toggled here. Now I don't know which one of these pins is I assume this is the full 8-bit thing. Let's connect these all up to this 8-bit maker to go ahead and get our saved byte. This is going to pass through to our output here. This is going to be our output byte. And then we want to enable this only if this input is enabled up here. So let's go ahead and connect that. So now that toggles that. If we were to set some of these values here and save, then on the next tick, it should pass it through. All right, and that looks like that did it for us. That has unlocked an 8-bit register, so we now have 8 bits of memory. Perfect. Let's go ahead and do the counter. Counting is so fundamental, even insects do it. From counting, species can evolve to compare and do arithmetic. And before you know it, you have apes building computers. Make a device that counts increments once per tick. Build a counter that will increase by 1 each tick. Additionally, there should be an option for overriding the counter with a given value. You were given 2 inputs, a bit and a byte. The bit input should toggle between counting and overriding the value of the byte, and the byte is going to be the other input. Okay, so for this counter, we're going to have to use a combination of things. Let's start by thinking about this 8-bit register that we have, because this can store a value for us, and it can also load and output a value. So let's just go ahead and start with this output value here is going to connect up to whatever's stored in this 8-bit register. And what we're going to have to do is figure out a way to store in this register what we want, either the overwritten value or the previous value plus 1. So we know we're also going to need to choose between those two things, the overwritten value or the previous value plus 1. So we're going to need a multiplexer to select between those two different values. So our 8-bit register here, this bottom input is going to be our save value. So let's go ahead and connect up this multiplexer here. This is going to be whatever value we want to pass through, and that's either going to be this input value here, which is our overwrite. Let me go ahead and label that, or it's going to be the previous value plus 1. So let's go ahead and figure out how to get the previous value plus 1. Now whatever output of this is going to be the previous value, and we need to add 1 to it. So let's get our 8-bit adder. We're going to need that. So let's make the first input here the previous value, and we need to add 1 to it. So we're going to have to use this 8-bit maker trick again. Let's go ahead and connect all of these here with off values for all the places except for the ones place, which will connect with an always on. So this value should always be 1. This is going to add those two values together. So our previous value plus 1, and let's take the output of that, and that's going to be the second input to our multiplexer. So now our multiplexer is going to select between the previous value plus 1 or this overwrite, and we need to toggle based on this input right here. So if we connect up this input to the multiplexer, this should now select between this overwrite value or the previous value plus 1. Now, in order to actually get it to output, we have to do something with these save and load values. The save input here will determine whether or not the register will save this new value, and the load determines whether that value gets written out here. And we want this to be on all the time. So let's take it on, because we always want it to write out this value, and we always want it to accept either the new overwrite value or the previous value plus 1. So it's always going to be writing something new to this register. So let's go ahead and connect that up here. So now it should always be outputting what's currently stored in the register, and it should always be updating the register on the next tick with either the overwrite or the previous value plus 1. So let's try and run this. Let's just do a couple ticks here. Action, add 1, desired output 0, current output 0. And then we see on the next tick that 1 is being output. Now it's going to update and store 2, because 2 is the next value of 1 plus 1 is going to be 2. 2 gets passed through. Now we're going to try to overwrite with 33. We can see that overwrite is set to 33. This overwrite input is toggled on, so it's going to pass through 33 here, which is the value that gets written into the register. And then on the next tick, we'll see that 33 output right there. So it looks like we're working so far. Let's go ahead and run the rest of the test cases and make sure this passes. Perfect. and that has unlocked the 8-bit counter. Next up is the 1-bit decoder. Create a component that can switch a signal between 2 pins. Okay, that sounds pretty straightforward. Output 1 and output 2. When the input is low, output positive to the first one. When the input is high, output positive to the second one. This seems really straightforward. I wonder if I'm missing something here. Should just need to connect that and that, right? We just negate the input for output 1, otherwise it's just the output. Let's just try that. That's pretty straightforward. 1-bit decoder just toggles between 2 outputs. Well, that was easy. Next up is going to be a 3-bit decoder. With 3 bits of input, there are 8 combinations. Make a circuit that selects 1 output for each of the 8 combinations. No more or less than 1 bit should be positive at a time. Okay, we're going to toggle between the output bits based on the number that corresponds to the input bit. Okay, for this 3-bit decoder, let's start by thinking about how we can group this up here. We have 2 groups of outputs. We have 1 through 4, and then we have 5 through 8. So we could think about this, if we look at our truth table, for input 3, if input 3 is low, we're going to output one of the bits 1 through 4. If input 3 is high, we're going to output one of the bits 5, 6, 7, or 8. So let's just take one of these decoders here. And this essentially is selecting for us which group of outputs to use. If input 3 is low, we're going to choose the top group of outputs, bits 1 through 4. We know we're going to output one of those. Otherwise, we're going to output one of these down here. Next up, let's think about input 2. If input 2 is low, we're going to output bits 1, 2, 5, or 6. And you'll notice that corresponds to the top half of each of these groups of outputs. So if the output of this, let's add another decoder here. If the output of this decoder is low, then we know we're going to output one of these 2 or one of these 2 down here. So we might be able to use some AND gates here. So for example, if we were to AND this together, and let's do another AND gate down here, and let's take this and pass it down there. What do we have here? So now, and let's say we were to connect these both up here. Now if input 2 is low and input 3 is low, we're going to output 1 and 2, and we're going to have to filter this down one more level in a second. Or we're going to output, if I was to toggle input 3, we would output 5 and 6. 5 and 6 here when input 2 is low. So this is getting us closer, but we're still not quite there yet. So now this is selecting the correct group of 2 within each block here, but now we also have to consider the other case. Okay, but what if input 2 is high? If input 2 is high, then we want to select 3, 4, 7, or 8. For example, let's look at 3 and 4. If input 2 is high and input 3 is low, so let's go there, then we would connect that up to 3 and 4. So if input 3 is low, but input 2 is high, then 3 and 4 are connected there. And then on the flip side, if input 2 is high and input 3 is high, right there, then we want to output here. Oh, I accidentally drew over something I shouldn't have. Then we want to output 7 or 8. Okay, so we're getting closer now. But right now, input 1 isn't affecting anything. So now if we look at input 1, we can see that if input 1 is low, we're going to choose 1, 3, 5, or 7. If input 1 is high, we're going to choose 2, 4, 6, or 8. And for each group of 2 here, if input 1 is low, then we're going to output on the first of the group of 2. So for this one and this one, if input 1 is low, we're going to output here. If input 1 is high, we're going to output there. Low, high, low, high, low, high. So we can do, again, something similar with these AND gates to help us decode this final level. Okay, we've hooked this all up now. Now we can see this other set of 4 outputs works. If we have this input 3 toggled, we're going to go to this group out here. If we have input 3 toggled high, then we're going to select from one of these bottom 4 output bits 5 through 8. If we have input 2, we're going to select from bits 7 and 8. And then finally, if input 1 is high, then we select bit 8. So let's go ahead and run this, and I think this will work. All right. We had our intern add a disable bit to this component. We were tired of looking at him running in circles and were looking for other pointless and tedious tasks to give him. Unlocks 3-bit decoder, toggles between 8 outputs. All right, that one was a bit complicated, but we figured it out. Little box. Can you fit 4 bytes of memory in this limited space? In this level, you have to build a circuit that can save or load from 4 different bytes of memory. You are given 1 bit that determines if you are to load, another bit determines if you are to save, and it comes with a corresponding value. Additionally, you have 2 address bits. With 2 bits, there are 4 combinations, 1 for each byte of memory in this level. The output has an enable pin, enable only on load. Wow, we really don't have much space here. So first of all, we need 4 bytes of memory. So that means 4 8-bit registers. And we need to select between these 4 based on our inputs. So let's make these upper 2 A, and let's make these lower 2 registers B, and then, so this is A0, A1, B0, B1. Okay, so the first thing we want to think about here is how do we address these? We have A or B, 0 or 1 right here. Going to be the relevant inputs. And let's start by thinking about selecting our outputs. So we could select between our outputs here by connecting this first one up. So here's going to be our A multiplexer out, and let's have our B multiplexer here. And then we'll need one more multiplexer to choose between A and B. And this, if we just need to connect up the signals here. So A, so this first toggle is going to swap between A and B. So let's drag this up here, and this is going to toggle our A or B multiplexer. Now let's take this input right here. This needs to connect as well. This is going to toggle between 0 or 1 within each of these multiplexers. So let's connect up our load signal here. Let's go ahead and turn that on just so we can see our outputs here. Oh, and we also need to connect this output pin to the load. The first thing we can do is we can actually connect the value to be saved. I think we can connect that to all of these input values, and what we want to do is toggle the save input right here only for the register we actually want to save it to. Okay, we've adjusted a little bit now. We have a little bit more space to work with. We can think a little bit about our decoders here. So let's connect up this A or B toggle here, connect it up to this decoder. And kind of like the last level, we're going to use this to specify which of these save inputs we want to be enabled. I have consolidated a lot of the space in here, so it should be a lot more compact, and we may be able to add this last level of AND gates that we need here. Okay, I've consolidated even more, and I might be able to do it now. Okay, I think this will do it. Let's run and see. Oh my, that was really complicated, but we managed to fit it all in there. That was a pretty challenging level right there. In our advanced civilization, forcing prisoners to do extremely menial tasks is slavery and is technically illegal. That is why we instead had our intern create the 256-byte version of your component. Oh my word, I could not imagine. That was just 4 bytes. I cannot imagine trying to do 256. Rip that intern. Unlocks 256-byte RAM memory component. Okay, that's some pretty big memory storage space there. Okay, that is the memory section completed. Let's move on to the final level in arithmetic, the logic engine. Create a device that can OR, NAND, NOR, or AND two inputs. The third input will be the instruction. An instruction is just what we call the number that determines what to compute. Our instructions are OR, NAND, NOR, AND, corresponding to 0, 1, 2, and 3 respectively, and for reasons that will be revealed later, you can't move the red components in the level. Let's start with a simple case in OR, 8-bit OR. Well, we have that right here, an 8-bit OR, bitwise OR two values. So let's just go ahead and connect up input 1 and input 2 here, and that should be our, let me go and label this. And did we have to do NOR? We do have to do a NOR. And NOR is quite simply the not, or it's the inverse of an OR. So that's OR and NOR completed, and we don't have an AND. We could either split this up into individual bits and AND them all together. We don't really have much space to do that though. So let's see if we can think of a different way to accomplish this. Now, I want to revisit something that we hit on the very first episode, De Morgan's laws. Based on De Morgan's laws, you can essentially get to any of the other basic logic gates by just inverting the inputs and outputs. So if you were to take an OR gate and invert the output and also invert the input, that would be the same thing as doing an AND. Or in our case, what we probably want to do, because we need to get both a NAND and a AND, we'll invert the inputs to get the NAND, and then we'll invert the output of that to get the AND equivalent. So this right here should be the NAND. And then if we were to draw another wire up here, that's not this, this should be the AND. That should be all of the logic that we need. But now we have to choose which output we're going to use to actually pass through, and that's based on this input. Okay, so if bits 0 and 1 are low, we want OR. So we're probably going to have to split this up, and we only care about bits 1 and 2 here. So what we need is multiplexers. So we're going to need one more multiplexer here. Okay, so let's go ahead and test this to make sure that this is working. Right now we can see that the code is OR, and we see that the value of the OR logic is getting passed through to the output. Next up is NAND, and it looks like actually the value of the AND is what's getting passed through. So we got our logic backwards here. I think we can take our NOT gate and let's just move it a little earlier. Let's take this NOT and put it right here. So now the output of the NAND is getting passed through. NOR is getting passed through now when the code is NOR, and finally AND is getting passed through. So I think that has solved it for us. Let's go ahead and run and make sure this works. All right, there we go, and that has unlocked the 8-bit AND, 8-bit NAND, and 8-bit NOR. So that's a lot of very helpful components that we'll definitely use in the future. All right, and with that, we have finished the arithmetic and the memory sections, and we are ready to move on to CPU architecture, but that will have to wait for next episode. Thanks for tuning in, and I'll see you next time.